Welcome back. So where I left off, we said that we had this, I guess we could call it equation, or this function, although I didn't write it with the function notation, where I said the distance is equal to 16t squared, and I graphed it. It's like a parabola, right, for positive time. And then we said, well, the velocity, if we know the distance, the velocity is just the change of the distance with respect to time. And since the velocity is always changing, you can't just take the slope. You'd actually have to take the derivative, right? So we took the derivative with respect to time of this function, or this equation, and we got 32t, and this is the velocity. And then we graphed it. And then I asked a question. I was like, well, we want to figure out if we were given this, if we were given just this, and I asked you, what is the distance that this object travels after time, after 10 seconds? Let's say this t0 is equal to 10 seconds. I want to know how far has this thing gone after 10 seconds. And let's say you didn't know that you could just take the antiderivative. Let's say we didn't know this at all. And let's say you didn't know that you could just take the antiderivative, because we just showed that the derivative of distance is velocity, so the antiderivative of velocity is distance. So let's say you couldn't just take the antiderivative. What's a way that you could start to try to approximate how far you've traveled after, say, 10 seconds? Well, what it says is you graph this, and you say, let's assume over some change in time. Let's assume over some change in time, velocity is roughly constant, right? Let's say velocity is right here. So you could approximate how far you travel over that small change in time by multiplying that change in time, let's say that's like, a millionth of a second, times the velocity at roughly that time, or maybe even the average velocity over that time. And you would get the distance you've traveled over that very small fraction of time, right? But if you look at it visually, that also happens to be the area of this rectangle, right? And what we said is if you wanted to know how far you travel after 10 seconds, you just do a bunch of these rectangles, and you sum up the area, right? And you can imagine, and you don't have to imagine, it's actually true, the smaller the bases of these rectangles, and the more of these rectangles you have, the more accurate your approximation will be. And you'll approach two things. You'll approach the area under this curve, right? Almost the exact area under this curve. And you'd also get almost the exact value of the distance after, say, 10 seconds in this case, right? But 10 didn't have to be an exact number. It could have been a variable. So this is something pretty interesting. All of a sudden, we see that the antiderivative is pretty darn similar to the area under the curve, and it actually turns out that they're the same thing. And this is where I'm going to teach you the indefinite integral. So the indefinite integral, I don't know how comfortable you are with summation. I remember the first time I learned calculus, I wasn't that comfortable with summation. But it's really, all the indefinite integral is you can kind of view it as a sum, right? So now you'll maybe understand a little bit more why this symbol looks kind of like a sigma. That's actually how I view it. And please look it up so you can see properly drawn integrals. But in this case, the indefinite integral is just saying, well, I'm going to take the sum from t equals 0, right? So from t equals 0 to, let's say in this example, t equals 10, right? Because I said 10. From t equals 0 to t equals 10. And I'm going to take the sum of each of the heights, the height at any given point, right? The height at any given point, which is the velocity, and then what's the formula for the velocity? It's 32t. 32t, and then I'm at times the base at each of these rectangles, dt. And so this is the definite integral. The definite integral is literally, and they never do this in math texts, and that's what always kind of confused me, is that you can kind of view it like a sum like this. It's kind of the sum of each of these rectangles, but it's the limit as it's, if we actually had, if these were discrete rectangles, you could just do a sum, and you could make the rectangle bases smaller and smaller and have more and more rectangles, and just do a regular sum. And actually, that's how, if you ever write a computer program to approximate an integral or approximate the area under curve, that's the way a computer program would actually do it. But the actual indefinite integral says, well, this is a sum, but it's the limit as the bases of these rectangles get smaller and smaller and smaller and smaller, and we have more and more and more of these rectangles. So if as these dt's approach 0, and then the number of rectangles actually approach infinity. So I'm actually I'll do that more rigorously later, but I think it's very important to get this intuitive feel of just what an integral is. It isn't just this voodoo that happens to be there. But anyway, so just going back to the problem. So the integral this is now a definite integral. We're saying from t equals 0 to t equals 10. This tells us two things. This tells us the area of the curve from t equals 0 to t equals 10, right? It tells us this whole area. And it also tells us how far the object has gone after 10 seconds, right? So this is very interesting. The indefinite integral tells us two things. It tells us area, and it also tells us the antiderivative, right? We're already familiar with it as an antiderivative. So let me give you another example, or actually maybe I'll stick with this example, but I'll clear it a bit. Actually, maybe I should erase. Actually, erasing might be a good option with this one, since it's fairly messy. I think you know all this stuff now. I just need space. Maybe. Okay, so we have that indefinite integral. And we can actually figure it out too. I mean, well, after t seconds, and the way you evaluate an indefinite integral, and let me show you that first, is that you figure out the integral. So let me continue with the problem actually. As you can tell, I don't plan much for these presentations. So the way you figure out the indefinite integral is you say, and sometimes they won't write t equals 0 to t equals t. They'll just say from 0 to 10 of 32 t dt, right? And the way you evaluate this is you figure out the antiderivative, and you really don't have to do the plus c here. So the antiderivative we know is 16t squared, right? It's 1/2 t squared times 32, so that's 16t squared. T squared. And we evaluate this at 10, and we evaluated it as 0. And then we subtract the difference. So we evaluate this at 10, so 16 times 100, right? That's evaluated at 10. And then we subtract it, evaluated at 0. So 16 times 0 is 0. So after 10 seconds, we would have gone 1,600 feet. And also, the area under this curve is 1,600. Is 1,600 actually? I guess, yeah, it would be 1,600. So let's use this to do a couple more examples. And actually, I'm going to show you why we do this subtraction. Actually, I'm going to do that right now. Let me clear it. Oh, that's ugly. Okay. I'll now do it more general, actually. Let me draw this twice. Once for the distance and once for its derivative. So let's say that the distance, yeah, well, let's just say it looks, let's say it looks something like this. Let's say you start at some distance, and then it goes up like that, right? So let's say we call this distance b. Well, let's just call this, I don't know, 5. Right? We start at 5 feet, and then we move forward from there, right? And this axis is of course time. This axis, maybe I shouldn't do 5 because it looks so much like s. That's 5 feet, and this is the s, or distance, axis. And actually, I just looked at the clock. I'm running out of time, so let me continue this in the next presentation.